folks, welcome back to Physics with Captain Rod. I'm making this video to demonstrate again how to apply momentum concepts and also to tie it in with work energy types of concepts. So in this example, all right, imagine we've got this arrow right here moving along at 100 meters per second. And I drew the velocity vector in blue just to distinguish it from the actual picture of the arrow. And that arrow has been fired at this target here. I suppose I got to put the bullseye in the target. And imagine that the arrow hits the target, and then the whole system slides 6 meters until it stops here. Again, there's my target there. I got a bullseye. So we're going to kind of analyze this system, and just to throw out something to calculate, I guess we'll try to find the frictional force and the coefficient of friction between the target and the surface. So one of the important things here when analyzing these types of problems, I like to imagine a digital camera taking like 1,000 snapshots while this happens. The time frame for the arrow to hit the target and then the whole thing to slide to rest. This is a very small time, a second or so, or maybe less. Imagine, say, 1,000 digital snapshots, and there's really 3 important pictures that are very important. I've already got the first one here. I'm going to call this picture 1. This is just an instant before arrow hits the target. Right. Another very important picture that we'd want to kind of pull out of that camera is an instant after the arrow hits the target. So I'm going to draw this kind of down below. Here's the target. Arrow has hit it. The whole thing is moving to the right now. I guess since I already drew velocity vectors in blue, I'll stick with that. So the whole thing is moving to the right with a speed that I'm going to call v2 here for velocity of the arrow, picture 2. So again, you have to imagine this picture basically right on top of this, moved over just 100th or so of a meter, just barely. Okay, it's a difference in time. So position 1 right before impact, position 2 here just after the impact, and then position 3 is going to be after the system has slid to rest. Right? So now we've really got 2 different stages in this problem to consider. We got to consider 1 to 2 and then 2 to 3. So from 1 to 2, this is an impact, and it's very important to understand conceptually, how the forces interact between the arrow and the target. So in that time frame where the target is picking up speed and the arrow's losing speed, the force exerted, if I were to draw a picture of this, on the target is to the right. Right? And then the arrow's part of the interaction here, and the force exerted on the arrow is to the left. And again, that force is the interaction between the arrow and the target. The important thing is that the net force on the system is 0 as long as we consider both at the same time. So that's what allows us to write a momentum conservation for this problem. So conservation of momentum from 1 to 2 in the x direction. I'm just going to put a little right positive here to indicate that. And we're going to have the initial momentum of the arrow. I'm going to call that MAVA1 for mass of the arrow, velocity arrow, picture 1. Right? The target is not moving in picture 1, so it doesn't have a momentum. If you want to put +0, that's perfectly fine. Right? So here's the momentum for the arrow, picture 1. That has to equal the momentum of the system after the impact. Now these are acting like one mass. They're stuck together. So I'm going to go ahead and, I guess we'll call that T for target. So the mass of the system is mass of the arrow plus mass of the target times the velocity v2. So this should be reasonably easy to solve for v2. I'm going to go ahead and put numbers in. It doesn't really matter in this equation whether we put the masses in grams or kilograms. It's just going to divide out anyway, but I'll go ahead and put them in kilograms. And I'm also going to put a little NCU here for note consistent units. So mass of the arrow is going to be 0.05 kilograms. All right, that's the 50 grams converted at 100 meters per second. I'm going to go ahead and put those units in. Equals mass added together is going to be 2.05 kilograms times V2. Now you may wonder, why would I put the units on the velocity and not the mass? Well, I just took note that if these are both in kilograms, they're going to divide out anyway. I was putting the units in to show that velocity will come out in meter per second. If you could just hold on one moment, I've got to answer my door. So I'm back, and while I was taking my little break there, I actually went ahead and calculated V2. So I ran the numbers here, and I got V2 of approximately 2.4 meters per second. So that's the predicted speed based on momentum conservation after the impact. Now we need to consider what's happening between pictures 2 and 3. Now from 2 to 3, there's a couple ways we can handle it. We could use the 2.4 meter per second, the 6 meter, write a velocity graph, use the distance and area and stuff like that to calculate time, and then the acceleration, go to a free body. I'm going to go ahead and just write out the work energy theorem from 2 to 3. So PE2 plus KE2 plus work equals PE3 plus KE3. Okay. I'm going to take note that there are no changes in potential energy, no springs to worry about. So basically, if we just put a datum right through here, all potential energies are 0. Position 3 is stopped, so KE3 is 0. So what we're going to have is 1/2 mv2 squared. I'm going to leave that work term blank for a minute. Equals 0 potential plus 0 kinetic. Now that blank term, that work term, let's take a look at a free body of this block, and again we're looking at the block while it's sliding to the right. Right, so there's a picture when its velocity is to the right. Now if I start looking at the forces, we've got the gravitational force down, a normal force up, and what stopped this block is some sort of frictional force, which would be to the left on this block. Now work terms. Work is force times distance, but only forces in the direction of motion do work. So as I look at these three forces, the normal doesn't do any work because it makes a right angle to the velocity of the particle. Same thing with the mg. The friction does, however. Work done by the frictional force is going to be minus F times D, minus because the frictional force is to the left, but the block is moving to the right. And I think we can go ahead and find the frictional force from this. I'm going to go ahead and just solve this for F. We're going to have basically mv2 squared over 2d. And I'm going to go ahead and just kind of run the numbers here. Now the mass, I probably should have took note of this. The mass is the sum of the two masses because the arrow is part of the system at that point still. So what we're going to have here is 2.05. There's 2.4. Squared, divided by 2, divided by 6. Okay. I think I'm going to have to run this again here. Hold on, I think I screwed this up. Okay, I'm back here. So I've ran that a couple times here, and I get, for a frictional force, I get 0.98 newtons. Now, that's a rounded value, and I used 2.4 meter per second for my speed. This would have worked out a little more accurate had I carried 1 or 2 more decimals, but again, this is just an example for demonstrating concept here. So I got a frictional force of about, right around 1 Newton that stopped this thing. Now, to get the frictional coefficient, I'll just take note that the frictional force is equal to the coefficient of friction times the normal. So the frictional force we just found to be 0.98 newtons. The normal, now here's where we would look at our free body, right? So as I look here at these forces, I would take note that if you sum forces y direction, we're going to get 0. This thing's not accelerating up. So basically the normal is equal to mg, which is going to be 2.05 kilograms, that's the mass of the system, times the 9.8 Newton per kilogram or meter per second squared, your choice. If we go ahead and solve that for the frictional coefficient, I get 0.049, or I'm just going to round that to approximately 0.05. So this is a pretty icy surface, it looks like. Again, the important things here are recognizing that there's 3 important time frames, right? Time 1, right before the impact. Time 2, just after the impact. Time 3, after the system has stopped. Right? Another important thing is knowing what concept to apply where. Whoop, just one moment. Okay, sorry about that. Busy person here. Got students needed help. So, let's see, where was I? 1 to 2 is an impact. So impacts typically will start with momentum. Key concept there is that during an impact, the interaction force between the two or multiple objects is between them is 0, at least net force is 0 if you consider the entire system. If you, in this case, if you consider both objects part of your system. So that's what allows us to write momentum conservation. And then from 2 to 3, we can recognize that the kinetic energy of the system is being dissipated or changed by a frictional force doing work, and that's what allows us to write this work energy theorem. Again, we could have also drawn a velocity graph and kind of worked it that way. But anyway, I hope this is a decent example of how to apply these concepts, and have a great day.